Okay, let's get started with class for today. Does anyone need the notes that I handed out on Monday? I'm not gonna go all the way over it. Can you we'll meet around. Anyone else? Okay. Yeah, so we're finishing up chapter 6. We just have this one final idea of these positive definite matrices. And we haven't really gone into like the most important properties of them yet. So again, what these positive definite matrices are is they're going to be symmetric matrices that have positive eigenvalues. Again, in section 6.4, we showed that the symmetric matrices always have real eigenvalues, so it makes sense to say whether or not they're going to be positive or negative. And so positive definite just means you have symmetric, and then all the eigenvalues are going to be positive. And then the less important definition is there's an idea of having semi-definite matrices as well, which is instead of having strictly greater than 0, this is going to be greater than or equal to 0. So you can have some that are equal to 0 as well. And so it's worth mentioning these positive definite matrices are always going to be invertible because all the eigenvalues are greater than 0, which means you can't have a 0 determinant. So the determinant's just the product of the eigenvalues. And so we went through a couple of examples. This one was kind of basic in that we wanted to show the following matrix was positive definite. So we just found the eigenvalues, showed that they were greater than 0. And so where I was moving with respect to, or kind of at the end of the lecture on Monday, is that there's going to be other ways of determining whether or not your matrix is going to be positive definite. So there's kind of 5 major ways of thinking about positive definiteness. And I originally underlined like the first, the fourth, and the fifth to, I guess, illuminate their importance. I kind of told you to gloss over the second and third ones. I will say, I think the second one is actually pretty valuable in determining positive definiteness. So maybe I should have just like said the original definition is probably like the least convenient of them all, I suppose. And I was talking about like these n upper left determinants, and it's kind of like, what are those? And like, why does it matter? Like these upper left determinants are really tracking the possible products of the eigenvalues that you can have. And this is also another like important quality in the sense that if you have, like this is also saying kind of wrapped up in this, is that if you take a determinant and it ends up being less than 0, that means your matrix cannot be positive definite. Because that's saying like if you have a determinant that's less than 0, it means at least one of your eigenvalues has to be less than 0. Right, so it's actually a pretty useful definition I wasn't thinking about before. But kind of what I was getting at is, like if I looked at this upper left determinant, that's just going to be 3. If I looked at this upper left determinant here, you can think in terms of, like, again, the determinant's going to be the product of the eigenvalues. And so if I take the determinant, it's going to be 33 minus 70, which is going to be less than 0. And so that means one of the eigenvalues has to be less than 0. So you can already determine it's not going to be positive definite from this. I'll do another example later on, but that's kind of the idea of what's going on with these upper left determinants. And again, if you took the entire determinant here, it's going to end up being less than 0. So that can tell you it's not going to be positive definite as well. And so we're going to go through a number of examples on the next page. Like I'm going to give you 4 matrices and you have to determine whether or not they're positive definite. And for the most part, it's not so bad at this point because we already know we can just look at the pivots, we can look at the signs of derivatives, or we can do these other things to determine if it's going to be or if it's going to be positive definite or not. And so before doing that, though, I want to prove the 4th and 5th properties here, because it's really the 5th property that's really going to carry over when we start doing singular value decomposition. When we're doing singular value decomposition, we're really going to be doing eigen decompositions on matrices of the form of A transpose times A. So it's like A transpose times A matrix is actually very important. And so we're actually going to do the proof on the next page first. So we're going to go to the top of page 4 and prove this proposition, and then we'll go backwards and prove this proposition here. I kind of forgot that you need the 5th property in order to show the fourth property, at least in a way that's not super long. And so we're going to prove the proposition at the top of page 4 first. So this is saying that if S is positive definite, then we have that F is equal to A transpose times A for a matrix A with independent columns. And so we're going to make use of the spectral theorem from section 6.4. So just as a reminder what the spectral theorem tells us. So from the spectral theorem, this is a good theorem to remember. This is kind of like the theorem that tells you that symmetric matrices are very nice to work with. So from the spectral theorem of section 6.4, because S is positive definite, again, wrapped up in the definition of positive definite is symmetry. So we know that S is going to be symmetric. So this implies that we have that S has a set of orthonormal eigenvectors. Eigenvectors that you can use to diagonalize S with. So because S is positive definite and thus symmetric, the spectral theorem tells you that it's going to have a set of orthonormal eigenvectors. So we can write S is equal. So when I have orthonormal eigenvectors, that means the matrix is going to be orthogonal. So I'm going to use Q instead of X. So Q is the matrix that's formed from the eigenvectors. So this is kind of like a special case. So I write it with Q instead of X. And because Q is orthogonal, because the column vectors are given by these orthonormal vectors, the inverse of Q is just given by the transpose. So this is going to be equal to Q, and then your diagonal matrix consisting of your eigenvalues, and then Q transposed. I'm just changing the Q inverse to the Q transpose. They're equal to one another in this case. And so we're really just making use of symmetry here, right? We're just making use of the fact that S is symmetric. And now we want to make use of the fact that S is positive definite. So because S is symmetric, we know we have this diagonalization in terms of orthogonal matrices. Furthermore, because S is symmetric, we know its eigenvalues are going to be real. And then because it's positive definite, we know the eigenvalues are also going to be positive. So what we can say is as S is positive definite, we can have that the eigenvalues, or we know that the eigenvalues are going to be positive. And then because S is symmetric, we can assume they're real numbers as well. So I'm going to say they're positive real numbers. And so what this means, so I'm kind of using the following fact. If I give you any real number, say like 5 or 7 or something like that, you can always find a number whose square is equal to that number, namely the square root. I feel like I don't have to write this out, but I don't know. I feel like if I just wrote it out, I don't know if it would be confusing to people. But the key point is, like, for any positive real number, you can always find a number whose square ends up being equal to that real number. Just find the square root, right? And so what this means is this is going to imply that we can write lambda as being equal to d squared, right? Where d is some diagonal matrix that's really just consisting of the square roots of your eigenvalues, right? So if I had the matrix like 5, 0, 7, 0, and this is my lambda, this is the same thing as doing the square root of 5, 0, 0, the square root of 7 squared. And so this would be equal to d squared, right? So I'm saying d is just the matrix of the square roots of your eigenvalues, in other words. And if I had more room, I would have explicitly, well, I guess I can write it out here. So this is saying, like, I'm just saying that d is equal to the square root of 5, 0, 0, the square root of 7, right? So it's really just like the square root of lambda, so to speak. Right, so we have lambda. You can find a d such that lambda is equal to d squared. And to wrap this all up, we're actually really close to the end. We have that s. So we had s was equal to q, and then lambda, and then q transposed. But instead of thinking about things in terms of lambda, which is the eigenvalues, we can think in terms of d, which is really just the square root of the eigenvalues. So you can rewrite this as being equal to q d squared q transposed, which you can then write as q times d times q transposed. And then this next part, it's going to look pretty dumb, but I'm trying, like, the goal is I want to be able to write s as a transpose times a. And this is kind of our a right here. So it's like we want to be able to express this product here as like a transposed. And so how I'm going to do that, this part looks a little bit silly, is I'm going to write it in the following way. So it turns out this is the same as having d transposed times q transposed transposed. If I distributed the transposed here, it would switch the order and it would get rid of the transposes, and that would just give you q times d. And then this is going to be times d times q transposed. And then the last observation here is D is a diagonal matrix, so the transpose doesn't have any effect on it. And so you can just rewrite D transposed as D. So this is the same thing as D times Q transposed times D times Q transposed. The reason why I'm kind of writing it out in this dumb way is if I let this be equal to A, then this matrix next to it is equal to A transposed, right? So if A is equal to DQ transpose, we have DQ transposed here, and then we have the transpose of that. So it's kind of like a dumb way of writing things, but it allows you to think about S as being able to be written in terms of A transpose times A. So it looks dumb here, but it'll be useful in the future, writing things out in this manner. And so it's worth mentioning that if you have a matrix of the form of like A transpose times A, it's always going to be symmetric. And so symmetric matrices are important, which is why we care about having something of the form of like A transpose times A. Okay. Yeah, so the main idea is you have this diagonalization, and because you have positive real eigenvalues, you can write out like the square root of lambda, which is really just the square root of the diagonal terms that you have, which I'm denoting by D. Any questions about this proof or like the idea? Yeah, so it's a lot of writing, but again, it's this diagonalization and then define the square root of lambda to be like the square root of the eigenvalues, like a diagonal matrix where you just do the square root of the eigenvalues. That's really the two main parts that's going on. And then you kind of rewrite things in this kind of silly way. Okay, so we're going to go back up and we're going to make use of this proposition to prove the next proposition, or I guess the proposition on the previous page. Oh, yeah, question.
For the last example, the last two lines, what changed between D transpose, Q transpose, all that transpose? So like right below that.
Yeah, the only thing I got rid of was the transpose that's being applied to D. Because like D is a diagonal matrix. So if you apply the transpose, like all the off diagonal terms will just be zero. So like it's just going to be symmetric. Like diagonal matrices are always symmetric, really by definition. And so I just got rid of this transpose, and that made it so these two terms are like these two matrices are the same as well.
Like,
any other questions? Okay. Yeah, the next example makes use of this proof, which is why I did things out of order. I wasn't careful when writing out the notes. And so for this one, this isn't really the most convenient way. Like if you're given a particular matrix, you usually don't want to use this proposition. But this proposition is useful if you're proving something more general, I would say. Could have utility. Like this is really going to be making use of the dot product in the sense that you have like an X transpose times X, which is kind of like the dot product. You just have a symmetric matrix in front that you kind of want to deal with. And so the proof of this is mostly just a corollary of the thing that we just proved. So as S is positive definite, from the previous proposition, we can write out S is equal to A transposed times A. So I'm going to say by the proposition below, which really means on the next page, I suppose. And then I guess there's one other piece of information that we're using here as well. And so we were saying that A had independent columns as well when proving this part here. So I guess I kind of did things in a strange way. Well, I guess S is positive definite, so you already know it's going to be invertible. So I guess I didn't have to make that observation that I just made. Anyway, so we know the following as well. So this is going to go back into chapter 3 stuff a little bit. So furthermore, and I guess chapter 4 stuff as well. So because S is positive definite, as I said in the beginning of class, this immediately means that S is going to be invertible because it has positive eigenvalues. None of the eigenvalues are 0, which means it's going to be invertible. So we can say that the null space of S, this is going to be equal to 0 because S, again, is going to be invertible. And by definition, we said that S is equal to A transpose times A. So we have that this is equal to the null space of A transposed times A. And then we showed in class, this is actually going to be a pretty important fact, especially when we do singular value decomposition. This gives you a way of thinking about like null spaces and row spaces. So we proved in section 4.2 that the null space of A transpose times A is equal to the null space of A. It was a longer proof, but we did it a while ago. So these null spaces are equal to one another, which also means their row spaces are going to be equal to one another. It's something we'll make use of probably sometime next week. And so this is saying that the null space of A is trivial, right? So there's not a vector X you can multiply A by to make it 0 aside from the 0 vector, which we're going to make use of very quickly here, or very soon here. And so thus we can say the following. So if we look at X transposed times S times X, because S is equal to A transpose times A, we can make the following substitution. This is the same thing as X transposed times A transposed times A, and then times X. And so what you can do is you can look at the following. We have X transpose times A. This is really taking the following. So this is the same as the, I'll just write it out instead of saying it. This is the same thing as doing A times X transposed times A times X, right? If I distributed the transpose throughout this product, you'll distribute the transpose to both terms and you'll flip the order, which would give you X transpose times A transposed. So these two things are equal to one another. And then this is a vector, like A times X is a vector, A times X is a vector. If you do a vector transposed times itself via matrix multiplication, that's just the dot product with itself. And so you can express if you have a vector dotted with itself, that gives you the magnitude squared. So this is going to be equal to the magnitude of A times X squared. And so the goal was we wanted to show that this is going to be greater than 0. And we showed that this ends up being equal to the magnitude squared. So this will be greater than 0 as long as this vector is not 0. And we showed that the null space of A is equal to 0. So the only time A times X is equal to 0 is when X itself is equal to 0. And so this is going to be greater than 0 whenever we have that X is not equal to 0. Because again, the null space is just the 0 vector. So you can say as the null space of A, is this equal to 0? Right, so it's really this part right here that serves as the proof. Everything else was kind of just set up. And so this part proves the result. Okay. Any questions about the proof of this proposition? Yeah, so this gives you a way of thinking about positive definiteness in terms of a dot product. Again, if you replace S with A transpose times A, this part always just becomes the magnitude of AX squared. So it gives you a length of some vector, which again has utility when doing singular value decomposition in the future. Okay, any questions before I move on? Okay. We're going to do some explicit examples now. And then I think there's one where you want to actually do this like factorization. So I'll give you a matrix S, and then you want to determine what A transpose times A is going to be. So this next example, I give you 4 matrices, and I want you to determine whether or not they're going to be positive definite using any of these definitions here. And if I give you explicit matrices, I feel like the easiest ways of showing it whether or not it's positive definite are really just going to be the first 2 here. Usually you don't want to, this is a bit more work down here. And then this third part, it's easier to just find the pivots than it is the eigenvalues. So I wouldn't recommend using it. That said, the first one, I do want to use one of the more unorthodox checks. So like this S1, I'll spoil it and say that it's not going to be positive definite. And I'm going to show it's not positive definite using this definition. And then the other 3 we'll do it the more easy way. And I'm going to ask you to solve them for me pretty much. But S1, I'm going to do it in the way that's a little bit more unintuitive. So if I look at S1, I'm going to use the 4th definition, i.e. this like X transpose times S times X, and show that it can be equal to 0 for vectors that are not, that are non-zero. And so I'm going to say the following. We're going to observe that we have that X transposed. Maybe I should say what X is going to be equal to. So I'm going to let X be the following vector. It's just going to be X1, X2. So these are just real numbers. Really variables, we don't know what they are. We can plug in values eventually and see what they're going to be though. And so if I do X transposed times S1 times X, it would be equal to the following. You would get X1, X2, you get 5, 6, 6, 7. And then you'll get X1, X2. And so if you go through with this matrix product, you end up getting entries that are going to give you, well, various polynomials. The highest will be a quadratic polynomial. Let me do it kind of step by step, actually. So this will give you X1, X2. If I multiply these 2 matrices together, this will give you 5, X1 plus 6, X2. And then this is going to be 6, X1 plus 7, X2. And so now if I perform this matrix multiplication, it's going to give me a quadratic polynomial. So all the terms are going to be order 2. This is going to be equal to 5x1 squared plus 17x1 x2. Or not 17, I think it's 12, and I just have bad handwriting in my notes. And then this is going to be, so I think you do like a 5 plus a 7 or something like that. And then that's going to be 7x2 squared. Oh yeah, it would be 12, I think. Okay, I'm just going to say it's 12. Anyways, so this is, you get this quadratic equation. It's like an order 2 polynomial on 2 variables, because like the degrees always add up to 2. This is like 2, 0. This is 1, 1. This is 0, 2. And I might talk more about quadratic forms and positive definite matrices in the future. But it turns out you can plug in certain values into x1 and x2 that are going to make it so this ends up being equal to a negative number. So this ends up being negative for a lot of values, but you just need to find one set of values that makes it negative. So it ends up being negative for x1 is equal to 4. So x1 is equal to 4. And then you have x2 is equal to minus 3. I think it ends up being equal to minus 1. And there's a bunch of other values you can plug in that's going to make it so this thing ends up being negative. Really, like where the negative aspect can come into play is the fact that you have like x1 times x2. So like this will always be greater than or equal to 0. This will always be greater than or equal to 0. So it's a matter of making sure this part kind of overpowers this part and this part. So you can have like, if x1 is negative and this is positive, then this is going to end up being negative. which is where problems can arise, right? And so this ends up breaking the fourth condition. So this implies that S1 is not positive definite. So this is kind of the hard way of going about it. I did want to go through at least one example where you look at this product, but for the other three, we're gonna use like the easier methods, I suppose. Before I go on to S2, S3, and S4, are there any questions about S1 at all? Okay, yeah, so we'll go on to S2. So for S2, does anyone see why this is going to be, well, I guess I should ask first, does anyone see if this is going to be positive definite or not positive definite? I saw your hand.
No,
Yeah, it's not going to be. And then why is that?
the first pivot is negative.
Yeah. So you can already, before doing any row reduction, you can already see we have a -1 here. So the first pivot is negative. So that means it's not going to be positive definite. And you can go further if you wanted to. It's unnecessary, but we have the matrix -1, -2, and then -2, -5. And so if you wanted to row reduce, again, it's not necessary. It would row reduce to -1, -2, and then 0, -1. So you can look at the two pivots, or really just any one of them. We have the -1 from before, that's less than 0. This is -1 as well. So you have negative pivots. Which implies that it's not going to be positive definite. I'm just going to say pos def, I guess. Again. Yeah, so you can see this check's a lot easier than doing like the first check that we did. S3. Any ideas about S3 as to whether or not it's going to be positive definite or not? Yeah, go ahead. Yeah, or yeah, so that's one way of saying it. Like this is not an invertible matrix, right? In order for you to have a invertible, or in order to have a positive definite matrix, it has to be invertible. So you end up getting a 0 eigenvalue is another way of saying it. But with S3, you can just note that it's not invertible. You can also check the determinant, right? If I took the determinant of S3, this is going to be equal to 100 minus 100, which is equal to 0. And if you look at the second statement, it says that the upper left determinants are going to be positive. So one of the upper left determinants is just the determinant itself, and we see it's equal to 0. So here it's not invertible, meaning it's not positive definite. You can also look at the determinant as well. Okay, and then the last one, which I guess could be positive definite or not. I was looking at the wording and say, which of the matrices are positive definite? The answer could be none of them, actually. So let's see what happens. What about S4? Any ideas on S4? Is it positive definite or not? Yeah, it is. I think I heard someone say it's positive. Yeah, so it is going to be positive definite. Again, you could do row reduction. I mean, it's the same example from before, except I added 1 to the 100 here. This is going to make it so the determinant is greater than 0. And you only have 2 eigenvalues. Well, I mean, you could have 2 negative eigenvalues that multiply. Anyway, so I'm going to just look at the pivots, I guess. So if you do like the matrix 1, 10, 10, 1, 0, 1. If you were to row reduce this, you can row reduce it to 1, 10, 0, 1. So this is going to be positive definite. You can see the eigenvalues are just going to be 1, 1. So you have 2 eigenvalues that are equal to 1. I don't know why that showed up. They're both greater than 0. So this is going to be positive definite. Handwriting's so bad. Positive definite. Right, so that's usually how these things go. Right, so I mean, maybe it looked bad when we were going through the proofs or I was going through this example, but as long as you can find the pivots, which you should, because you should know how to do row reduction at this point in time, you can see finding whether or not it's positive definite. So. Okay, any questions about any of these examples? Okay, so the last thing I want to go over from this section before going into the singular value decomposition is going into this idea of taking a matrix and then being able to express it as A transpose times A. So we did a proof, like that was the first proof we did today, was showing that if it is positive definite, then you have the ability to do this. And so you kind of want to reference the proof that we did earlier in order to determine like what is A, like where is this A coming from? From the proof we did earlier, when we can say S can be expressed as A transpose times A, we found that A ended up being equal to D times Q transposed, where Q was a matrix whose columns were given by the orthonormal eigenvectors. And then we had that D was kind of like the square root of sigma. And so that's the first thing I'll note here. So from the proof, we want to make use or reference the proof here. So from the proof at the top of page 4, we have that A is going to be equal to the following. We have that A is going to be equal to D times Q transposed. So where's the D in the Q transpose coming up from, or coming from? Where we have that S is equal to Q lambda Q transposed. Again, this is the eigen decomposition or like the diagonalization of S because S is symmetric. So we know we can diagonalize it using these kinds of matrices. And then you can rewrite lambda, I said sigma, lambda as D times Q transpose. Right, so that's where this D comes from, and that's where the Q comes from, right? It's this decomposition, or like the eigen decomposition. And so I'm going to skip some of the steps. So the first couple of steps is you really want to determine what Q is going to be, and you want to find what lambda is going to be. So you need to find the eigenvalues and the eigenvectors. And so I'm going to skip this part because at least looking at the exam, it seems like people are pretty comfortable with this part. So this is one can show that we're going to have the following eigenvalues and eigenvectors. So the first eigenvalue I'm going to say is going to be 4, and the other eigenvalue is going to be 2. So there's nothing tricky about finding the eigenvalues. You take the determinant, set it equal to 0. You get a quadratic polynomial that you can solve for. And then the corresponding eigenvectors are going to be the following. So the corresponding eigenvectors are going to be V1 is going to be -1, and then 1. And I'm going to make it so it's going to be normal, right? So we have a symmetric matrix. So we know the eigenvectors will be orthogonal to one another. And I'm just going to make it so they have unit length. So that way we can say they're orthonormal. So you get like an orthonormal basis of eigenvectors. So if I divide by the magnitude, I get Q1 is equal to 1 over the square root of 2. And then you get -1, 1. Right? So this is one of your eigenvectors. And then the other eigenvector is going to be the following. So the other eigenvector is V2, which is going to be equal to 1, 1. Which again, if I make it so it's going to be normal or of unit length, this will be 1 over the square root of 2, and then you get 1, 1. And you can see these vectors form an orthonormal basis, right? If I do -1, 1 dotted with 1, 1, you get 0, and they're both length, like unit length. So you get an orthonormal basis. When we're writing out S using this decomposition here, I'm making the assumption that the column vectors of Q are orthonormal, right? Like this works when the vectors of Q are orthonormal, which is why I'm going through this process right here. Okay, and so that's how we define Q. So we let Q be equal to the matrix whose column vectors are given by the eigenvectors we just found. So this is going to be -1 over the square root of 2, 1 over the square root of 2. And you can factor out the square root of 2 and just write it once instead of writing it over and over again. So this is our Q. This is going to be an orthogonal matrix because the columns are orthonormal. This is something we showed earlier in class or in the semester. And so we have that Q inverse In this case, is this going to be equal to the transpose of Q? And if you take the transpose of Q, well, it's symmetric. So this is going to be equal to the same thing over again. So it's minus 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2, and then 1 over the square root of 2. Right, so this is Q transposed here. That was one of the vectors we cared about finding. The other, or not vector, this is one of the matrices we cared about finding in order to determine what A was going to be equal to. And then the other matrix we cared about was this matrix D here. And so we define D to be equal to the square root of lambda. And so lambda is just a diagonal matrix consisting of your eigenvalues. So this is going to be 4, 0, 0, 2 to the 1/2 power. And so this is going to be equal to 2, 0, 0, and then the square root of 2. And so thus we have the following. So we have the two matrices we wanted to find. So we have A is equal to D times Q transposed. So this is going to be equal to 2, 0, 0, square root of 2. And then you're multiplying by this Q transpose that we had here. So this is minus 1, square root of 2, 1 over the square root of 2, 1 over the square root of 2, and then 1 over the square root of 2. If you perform this multiplication, you're going to get the following. So it's going to be minus the square root of 2, square root of 2, and then 1, 1. And so this is what the matrix A ends up being equal to. It's this one right here. And then you can always check your work. I'm going to kind of write out the general steps of what this would look like. So what should end up happening is we should be able to show that if you do A transposed times with A, it should be equal to the original matrix S that we had. And so with the matrix A that we found above, this A transpose times A, this is going to be equal. So the transpose of A just means the first row becomes the first column. So this is minus the square root of 2 and then the square root of 2. And then the second row becomes the second column. So you get 1, 1. You then multiply by the original A that we had. And so if you perform this multiplication, you get the square root of 2 or minus square root of 2 times minus square root of 2. That's equal to 2. And then you do 1 plus 1. That'll give you a 3. Here, you're going to have minus square root of 2 times the square root of 2. That's equal to 1. Or minus 1 plus 1 will give you a minus 1. And then similarly, you'll find this is going to be minus 1. And then this is going to be equal to 3. And so this ends up being equal to the original matrix S that we had up here. Right, so this is how you can express S as the product of A transpose times A. Again, it's really just a matter of knowing this formula. A is equal to D times Q transposed, which we derived when we proved this statement above here. That was this part. So I'm not going to, well, I don't know. It's good to know that you can write symmetric matrices in this manner. But when I give you an explicit example, you usually don't want to write it in this way. You want to work in other ways, but it could be useful in more general proofs is what I would say. Any questions about this example at all? Yeah, so if you can find the eigen decomposition of S or like this diagonalization, I'm kind of using those terms interchangeably now. If you can find the diagonalization of S, A just comes about as a corollary, really. You're just making use of the pieces that you found in the diagonalization. No question. Okay. Yeah, so I'm going to be able to introduce a little bit. So that's the end of section 6.5. Now we're going to go into singular value decomposition. This is kind of a major result in linear algebra. And so I'm going to spend a couple of days talking about this. So like this section here is more about like the theory and like where the singular value decomposition is going to like show up or like how it's derived in the first place. And then next week, we're going to look at applications. So like next week, we'll look at a little bit into like data science, like principal component analysis and maybe like eigenfaces or something like that. So I'm kind of like mixing two books together. Like I'm using the standard textbook for this section, but then I'm also going to pull some material from chapters 14 and 15 from this book, like practical linear algebra for data science. So we'll look at like applications to, I guess, like all kinds of different things. Like, oh yeah, go ahead.
So will it be reasonable to read both 14 and 15 out of the current textbook, or could you provide us with the subsection for the
There aren't really subsections. Like these chapters are like about like 10 pages long or so. So like they're pretty quick sections or like pretty quick chapters. And like in the notes that I write, like I am incorporating these chapters or like the relevant material from those chapters in them. So you don't have to like seek out the book or anything like that. Because like on the final, I can't really ask you to do like principal component analysis or anything like that. So they would be like there's gonna be like programming. You're not gonna do like programming on like the homeworks or anything, but like on the notes, I'm gonna use like some Python programming to show what's going on. But I might maybe I'll put the PDF on the Canvas page or something like that. I don't know. It's an O'Reilly book, so it's a nice book. But yeah, I'm gonna incorporate the relevant material in the notes that I hand out, so you don't have to actually like read the book or anything like that. And any other questions before continuing? Yeah, so I'm just gonna go through kind of the broad strokes for now, and then we'll go into like why this stuff works in class a little bit on Friday. And so in this section, we're gonna discuss singular value decomposition, which is abbreviated as SVD. And so you can view SVD as a generalization of diagonalization that is always going to work. So we found before that diagonalization only really works when we have independent eigenvectors. Like if we have linearly independent eigenvectors, then we can find diagonalization. And that's kind of a tall ask. Additionally, when we were doing diagonalization, it was only working for square matrices, right? Like, well, the matrix itself didn't have to be invertible, but you had to have like an invertible collection of eigenvectors, which then forced the eigenvector matrix to be square, which then forces the matrix to be square. So what I'm saying is like these diagonalization, it only works for square matrices, but this singular value decomposition is going to work for any m by n matrix. So this decomposition is not going to be quite as nice in that the conditions we're imposing on the original matrix are going to be less nice. But there is a relation between SVD and diagonalization we'll get into. And so summarizing what we found before, we found that if a matrix A is diagonalizable, then we can write out that A is equal to X times lambda times X inverse, where lambda is a diagonal matrix of eigenvalues, and the columns of X are eigenvectors. Furthermore, we saw that if A is symmetric, this becomes particularly nice where we have that X is going to be orthogonal matrix, and we have that lambda has real terms along the diagonal. So we like symmetric matrices a lot. And so that kind of summarizes chapter 6. And so with the singular value decomposition, we have that for any matrix A. We're going to be able to write A as being U times sigma times V transpose, where we have that U and V are both going to be orthogonal matrices. So their column vectors are going to be orthonormal. And then we have that lambda is also going to be a diagonal matrix with non-negative entries called the singular values. And so it turns out these singular values, we're going to show this later on, the singular values are just going to be the square roots of the eigenvalues, which is kind of what we were doing before when we were looking at this like A transpose times A, right? We're taking this D, which was equal to the square root of the eigenvalues. So these were actually what are called singular values. And they're going to have nice relations with, or like some nice properties. Okay, and so it turns out these two decompositions coincide when we have that A is positive semi-definite. And we'll see how later on. So this picture kind of illustrates the big picture of the singular value decomposition without going into detail. And so where this matrix U is going to come up, or how this matrix U is going to be constructed, is the first, so depending on the rank of your matrix A, we're saying A has rank R here. So the first R columns of this matrix are going to be consisting of a basis for your column space, or really an orthonormal basis of your column space. And then we know that the left null space is orthogonal to the column space. So you can complete the last couple of columns by filling it in with the basis vectors of the left null space. So all these vectors would be orthogonal to one another, which forces them to be linearly independent. So this would be an invertible matrix. And then the sigma, again, is it's these singular values, which are just the square roots of the eigenvalues. But I haven't said what eigenvalues they're the square roots of yet. It's not going to be A. It's actually going to be A transpose times A. And then this VT, the transpose of V, the rows are going to be given by the basis of the row space. And then again, the null spaces are orthogonal to the row space. So you can complete the basis by filling in the remaining rows with elements of the null space. And so one interpretation of this singular value decomposition is they're really just putting together the four major subspaces we spoke about before and then forming various matrices from them. And the only thing that's really new is finding the singular values. So again, this is going back into chapter 3, like these are the four major subspaces. We're putting them all together to construct this decomposition. But really the nice way of articulating or thinking about singular value decomposition is going to be in terms of eigenvalues and eigenvectors. I think that's the more intuitive way of going through examples. And that's kind of how I'm going to construct this stuff later on. And so what you may have noticed is that the SVD reveals all four major subspaces of the matrix. All that's left is to find the singular values, as I said before. I think I'm going to stop there. There are some properties. I probably do have enough time to go through this, but I don't know. I would like to, I feel like it would be better to wait until Friday. So we'll talk more about singular value decomposition on Friday. We'll show some of the properties and how it's defined. And then there's also going to be a quiz on Friday. So it'll be like 3 problems, just like before. And I'll probably tell you a bit more about what the quiz is going to look like in an email tomorrow, just so that we can prepare a little bit better.